Let's go ahead and get off the XY plane and start looking at space curves and talk about the idea of line integrals in space. Now, suppose that C is a smooth curve parameterized by x equals x of t, y equals y of t, and z equals z of t, or t going from A to B. Or equivalently, we can write it as a vector equation of r of t equals xt I, ytj plus zt k. Now, the line integral is then, as you would probably suspect, is to integrate over the curve of f of x, y, z times the square root of dx dt squared plus dy dt squared plus dz dt squared dt, which is obviously I can write in much more compact form as f of x, y, z times the magnitude of r prime of t dt. Now, just as we saw with this idea of triple integrals, remember in triple integrals, when we had the special case where f of x, y, z equals 1, that resulted in the volume of the region that we're integrating over. Likewise here, for the special case where f of x, y, z is equal to 1, what we end up with is the integral curve 1 times the magnitude of r prime of t dt, which is equal to the integral over the curve square root of, well, all of this. I'm going to write all that down again. dt, all of this, which is what we use to find arc length of a space curve. So this boils down exactly to what you would expect it to be. So getting up off of the xy plane and into a space curve, the natural extension to that is probably exactly what you would expect it to have been. Because if I stayed on the xy plane, I would not have had that z component, and I would not have had that z component right there. Getting off the xy plane, I have to account for z, so I simply add those two components to what I'm doing. And again, this integral, I should actually finish this up, equals L. The length of the curve, or sometimes you may say S, depends what notation you're using.